All right. Today we're going to be talking about bioenergetics and metabolism, and we're going to start off looking at what is metabolic energy and ATP. So our first learning objective is to interpret the first and second laws of thermodynamics. Now, this should be a review for you at this point, so if you need more help, certainly contact me. But let's just dive in and review the aspects that we need. So, the first law of thermodynamics it states that energy is conserved. So, when you have a closed system, energy can be exchanged with the surroundings in form of work or heat. That energy can be exchanged from one form to another, but it can't be created or destroyed. That is always there. Consequently, when we get a conversion of energy, we refer to that amount of energy that is converted as enthalpy. Okay, so this is the heat that's exchanged between the system and its surroundings at constant pressure. This is a kind of a funny way of describing it, but it has to do with the way that we actually measure it. Okay, so here is an example of a um, solid, in this case, it's going to be a fatty acid that we are combining with oxygen, so we are burning it into CO2. So here we have a little chamber. That chamber has that material in it, so this is palmitic acid. There is an ignition source and oxygen in that chamber, and there is a piston holding a constant 1 bar pressure or 1 atmosphere pressure on um, this reaction chamber. Surrounding this, we have a jacket of water, and in that jacket of water, we have um, a thermometer. Okay, so what happens is we spark it, this stuff starts to burn, the gases are going to, or as CO2 is formed, it's going to expand this chamber, and some of that is going to produce a lot of heat. That heat is then going to be transferred into the surrounding liquid. After this reaction is finished, the gases will start to recondense as the temperature transfers to the water, and then you'll come back down, and what you have left over is CO2 and water. But the surrounding water jacket has an elevated temperature. Measuring the difference between the initial state and final state gives us a value that tells us how much energy we gleaned from burning palmitic acid. Again, this is kind of a roundabout way of doing it, but this is the best that we've got. And we have instruments that are extraordinarily accurate um, at looking at this. So keep in mind that when we talk about enthalpy, um, that we are talking about the energy gleaned under a very specific circumstance. This does not necessarily completely translate to what is actually happening in the body, because clearly we aren't physically and quickly burning palmitic acid. We tend to break it down much slower and more in a more regulated way. But this gives you an idea of how we glean that value. Now, the second law of thermodynamics um, states that the um, entropy of an isolated system will tend to increase to a maximum value. Okay? This is a measure of randomness or disorder in a system. Okay? So if we have a particular vessel here that has sucrose in it, so here we have the individual sucrose molecules, and we have it in a certain volume of water. If we then add on an equal volume of water that's pure on top of that, We start off with all of the sugar down in the bottom. Over time, it spreads out. And keep in mind that this is solely happening because each individual molecule is moving independently and fairly randomly. So it inevitably will end up in this spread out state. The reason why this is inevitable is just a pure matter of statistics. So here we have a box that has a membrane in the middle, and we have 4 different colored molecules. There's exactly one condition where we can have all 4 molecules on the left-hand side. If we then ask the question, well, how many conditions can we have where we have one molecule on the right and 3 molecules on the left? Well, we have 4 ways that we can achieve that. Equally, when we say, well, what happens if we have 2 on each side? There is 6 different conditions that can meet that circumstance. And again, if we look at the opposite of this state, we have 4 more conditions, right? And if we look at the opposite of the initial state, there's exactly 1 condition. So the reason why entropy exists, why this is an issue, is just simply because it's more statistically likely. Sure, we could walk into a room and all of a sudden have all of the air molecules to one half of the room. It's certainly possible. There's nothing stopping the air molecules from doing that. It's just not very likely. Okay? So, now hopefully you will be able to interpret the second and first laws of thermodynamics.